Welcome, everyone. So today we have a special guest, Chip Bobbert. Chip is going to talk to you guys about some really cool, exciting stuff that I think you're really going to appreciate. So I'm going to start out. I just want to tell you a little bit about Chip, and he can introduce himself too, but I just want to talk a little bit about his bio because it's pretty impressive. I think you guys are going to like it, and I think you're going to like what he has to talk about today. So Chip is a senior academic technologist and the architect of Duke University's Maker and Media Labs, which are called the Multimedia Project Studio and Collab Studio. So basically, he's in charge of the makerspace at Duke, a large makerspace. These are some of the largest 3D printing focused makerspaces in higher ed. He is a co-founder of the Construct 3D conference. Chip has a Master of Science degree from the University of North Carolina, Wilmington in instructional technology. And while he was at UNCW, he also worked in television as a television engineer in technical media operations and the production of educational programming. And Chip served as a Marine in the military for 7 years. So pretty impressive resume. We're talking to someone who's doing some really cool stuff today. I don't want to give away exactly all the stuff he's doing because I could. Chip, welcome.
Absolutely. Thank you for having me, Ray. This is it's exciting to kind of even digitally come back to UNCW and have some of these chats with you. I'm looking forward to the conversation.
No, absolutely. When I saw some of the stuff you guys have been developing over at Duke, I thought this is something I want to show people because it's really cool, it's really timely, and it's just really interesting stuff. And I think anyone interested in tech and my field would be really fascinated by some of the stuff you guys are doing. Okay, so now you work in this 3D printing lab, and I'm going to get to some of the cool stuff you're doing. But what does that mean? What does it mean to work? Why does a university have a 3D printing lab? Like, what do you guys do? What's it like there?
So a 3D printing lab is, we get into 3D printing kind of turns into a buzzword a little bit. So I'm going to demystify the term 3D printing and a little bit of my view on what that is. There's a bigger, broader term called digital fabrication. Digital modeling and fabrication is another way that you'll find it phrased. And there's actually a wonderful Wikipedia page about that if you're following along. And basically, this is the concept of using robotic making at sort of the desktop or laboratory level to be able to produce things. This gives us the ability and flexibility to use commonly available CAD tools to realize a device very quickly. So this is not a staged device. This is actually, you can see I'm sitting in my lab here. This is something I reached over and grabbed off of my 3D printer. I had a need for this particular piece to be able to squeeze a hand sanitizer handle. I designed that in CAD this morning. I clicked file print just like I would with a paper printer. And a few hours later, that part fell out of the front of the machine. That's an amazing power when you step back and think about it. This is really changing the way that education is done, especially engineering education and physical art as well. So a lot of any sort of academic discipline that requires a level of creation and a level of digital interaction, this has the potential to influence. So it's been an exciting project. I'm extremely fortunate to be working at Duke in a place that has allowed me to have this vision and work to realize that and present this lab for our students to use.
Yeah, you have a pretty cool lab behind you. That's an awesome office. That's a lot cooler than my office at work, and I thought mine was pretty cool. Like, that looks like an awesome workspace that you've got there.
It is. I hide in my little lab when it's time to do it.
Okay, so
it struggles to get me out of here at night. So
you guys are doing this stuff, normal 3D printing. You're working with educators, working with education, developing all kinds of neat stuff, and then boom, coronavirus hits. So everyone's all of a sudden working from home. All of society across the world shut down for a time period. We're starting to move a little bit past that, but you guys at your lab didn't necessarily shut down. You guys have been doing some interesting stuff during this time. So tell me a little bit about what happened when coronavirus hit. What instead of going and working from home and just taking the time off, what did you guys do?
So really, I'm going to step back again for a second before I sort of answer that question. Initially, when this hit, I mentioned earlier in our pre-interview that I had a desire to sort of, this is obviously a heavy technology field. I had this desire to stop for a minute, pause, take a breath. We had gone through this massive building phase for the last 6 or 7 years to create the program that we have. And whenever you do that as a professional, there's always a moment where you sort of sacrifice some of your professional proficiency or technical proficiency to some of the administrative duties that you're required to do. So I was really looking forward to stopping for a moment, refreshing some of my knowledge on some of the latest CAD and digital sculpting packages and going through some training and whatnot. But along with the coronavirus, we saw problems start to appear in the form of distribution, supply chain lines, manufacturing. A lot of that was breaking down. And we, obviously, it's pretty well documented everywhere. We rely a lot on foreign manufacturing to produce the goods that we consume in the United States. Well, that's an issue when some of those same countries were also impacted by this virus. Supply chains were significantly disrupted. Mm-hmm. And when that disruption happens with healthcare systems, that creates problems. Essentially, the people that are treating patients aren't able to get the tools and materials and supplies that they need to perform their duties. Mm-hmm. So digital fabrication offers some interesting opportunities there. You can use some of these tools locally to produce just about anything you want. So the same 3D printer that could produce adapters for filtration may also be able to be used to produce nasal swabs or to produce other filtration devices that adapt a specific existing PAPR suits and things like that. So we started to really take some of our printers and leverage them toward these manufacturing shortfalls that we saw that existed.
Okay, so you formed, I read that you guys formed some kind of coronavirus task force. Is that correct? So you started working with doctors and scientists. What was this team like? Like, who were you working with? What does that mean, a coronavirus task force?
Absolutely. So we started a response force, and we ultimately ended up calling it the COVID Response Task Force. Specifically to address some of the problems about shortfalls. We had multiple people approaching us regarding various stories that they saw online where people were using 3D printers and laser cutters and CNC machines and other tools to solve some of the local problems and needs for their healthcare professionals. So obviously we were kind of in the midst of addressing a lot of this pile of people that were emailing and calling and good Samaritans that wanted to help. We felt it necessary to gather the minds, if you will, the way that we do in academia, to talk about some of these things. And, maybe there are things that we should produce and maybe there are things that we shouldn't produce. So for example, face masks are class 2 medical devices. So there's some problems there when you start to think about what it is to produce those. And even though there are simplified devices online, we wanted to make sure that we were producing the things that were absolutely as effective as possible and met, standards. While other things like face shields, for example, are lower class or non-class devices that we could possibly produce in the lab and provide additional help to our healthcare support. So when we start to talk about the range of professionals that are necessary to produce anything, even like we see in instructional design, other fields, the first things that you want to do are gather your subject matter experts. Sure. And bring them, have that meeting of the minds. We're fortunate at Duke in that we are one of the few universities that has a health system attached to us. Sure. And that an engineering school attached to us. So we were able to pull in several of the world-class engineers that work here and gather their advice. We're able to pull in physicians from the health system to also advise on what we need, not just if we should be producing something and how we should be producing, but what those things should be. So that task force, that's how we evolved and that's how it came about.
Okay, cool. So you guys developed this task force. You came up with a few ideas. So why don't you talk about, I don't want to name all the stuff you guys have developed. You want to talk about, obviously you just talked about face shields. So I know you guys developed a face shield. Do you want to talk about some of the things that were decided upon that you guys have developed over the last few months to help out with?
Absolutely. So development within the digital fab space is kind of an interesting thing. So oftentimes there are community projects. It's very much like open source software. There are a lot of open hardware projects that people rely on. Face shields is probably our biggest project to date by scale of parts produced. So we initially started with the goal of producing face shields, which at the time you weren't able to purchase. There was a national plastic shortage. We weren't
Sure,
able
yeah, you couldn't buy anything anywhere.
Yeah, so we were just gobbling up whatever material that we could find and then attempting to modify some of the community designs that we were finding to meet our needs. So the face shields, again, we set forth with a goal to produce 70,000 face shields.
Wow.
Which is it's an
That's
incredible.
a lot. So I assume so you have to have do you have some like special printer that can do that? Because I know like the one I buy off Amazon for like $500 to $1,000 cannot produce 70,000 face shields.
Absolutely. So this is where the power of digital modeling and fabrication really starts to shine through. You can take the same models that you're 3D printing and move those over to other manufacturing techniques such as CNC milling or such as injection molding.
What is that? What does that mean? CNC? I see that you did develop some of the stuff using CNC. I have no idea what that means whatsoever.
So when we look at digital modeling and fabrication, we have a couple of different approaches for something. In general, across all of human existence, we manufacture things into two basic categories. There's either subtractive manufacturing or there's additive manufacturing now. So typically, if we are grinding and abrading something away, you are subtracting that out. So if you are carving a wood block, for example, that's a subtractive technique. You have a big pile of wood and you kind of grind that out.
Gotcha.
If you go back into early human existence and really start to think about additive techniques that existed back then, pottery is a good example of something that we'd be adding up. We'd be taking clay and adding it to a board of nothing and possibly rotating it to form a other useful thing. So those are kind of how we divide and break things out. So 3D printing is always an additive technique. We take plastic, molten plastic in this case, or other techniques such as resin, and we apply different processes to it to extrude or coalesce it with light beams or whatever into a physical blob that kind of extrudes off of a plate, much like that pottery wheel example. And then with subtractive techniques, we grind or cut and abrade things away. And now, of course, we can apply robotics and computers to that. So we have spinning blades that will kind of do that work for you. You put in a block of aluminum or wood or plastic or whatever, and we move that knife in precise directions and ways to sort of carve out the thing that we want to do. So when we looked at injection molding with those face shields, the 3D printers and additive techniques are great for prototyping because you can make just about anything you want. You can shape something to an infinite degree.
And there's a clear plastic to make a face shield that you can put in a 3D printer, like so it's clear like that.
So this is where some of the other techniques start to come into play. So I mentioned laser cutting a little bit earlier. We use a laser much like a knife. We're able to put in sheets of plastic and use that laser to carve that out, and then those sheets of plastic, polycarbonate in this case, becomes that lens that snaps around the face frame.
Understood.
So the cool thing about digital modeling and fabrication, as I mentioned, is that this is a highly portable production technique. So we were able to produce these on the smaller laser cutters in our lab and perfect that design. And once we had reached the point of perfection, we were able to engage local manufacturers, also with the same laser cutters that have larger workforces and dedicated staff, and use them to produce it. So we're basically, if you think about it, it's like printing your term paper. You click file print, you get something out of a machine. That's really the way Digital Fab kind of works. We click file print, and the manufacturer is able to have parts falling out of a machine for us.
Yeah, that's really amazing that it works like that. So when you develop something like this, and we can start, I want to talk a little bit about some of the other stuff you guys developed too, but so when you develop like these face shields, do you have to test them to make sure they, like, how do you know that they meet, like, what, I don't even know the standards, like WHO standards or FDA, or how do you know, like, how do you test those things? Like, did you test them? Is that what happened?
Absolutely. So we did test them. I'm going to use the word we, but this was really performed by another professor that we had working here. And this is where the strength of that group comes into play. So there's, as we find in academia, there's no one person that can do all
this stuff. Sure.
All of this. So we have a wonderful gentleman named Mark Palmieri that has a considerable talent with simulation and was able to bring our designs into a CAD package and analyze it from different directions and ways to make sure that it was up to spec. And of course, there are specs that are out there and published. ANSI is the spec body that we used for this. So within, even though we had frozen almost all activity at the university, our librarians were still here and on point and able to, pull that technical documentation for us. And he was able to analyze those and ensure that they actually met ANSI specs. So within the healthcare industry, face shields before the COVID epidemic, weren't really widely used, to my understanding. These were used in some fields like dentistry or possibly labor and delivery and some of the other areas, but they're not used in general practice. So we really had to look and understand how the practitioners were going through their other activities. We're fortunate that Duke has a wonderful simulation lab at our School of Nursing where procedures and practices can be done. So we invited a group of 25 nurses and doctors in to go through their various activities and face shields on them, so that we could see and understand what they were doing. And there are things like with face shields, just as an example, if you are, say, a metal worker grinding metal, you want a face shield that goes all the way around your head and protects you as much as possible. But if you're a doctor, you need to be able to put a stethoscope on.
Sure.
ANSI spec requires that it's going to move behind the sides of the eyes and almost surround the head 180 degrees. But we were building this in an attempt to almost barely provide the coverage that was necessary, so the other things that they had to put onto their head would still work. So there were other problems too when you start to think about it. So an N95 has two different elastic straps that hold it to your face. Our elastic straps, we did not want to interfere with those. We didn't want somebody to doff a face shield and accidentally yank off their N95. Sure. So there were a lot of, even though it's a very simple design, there were a lot of things that we had to think through in our adaptations of.
Yeah, that's really interesting. I'm surprised. And so what was like the time of, hey, let's develop face shields until, hey, we're actually printing these? Like, how long did that take?
It was about 3 days.
Oh my goodness. Everything you just described happened in 3 days?
Yeah,
I was thinking you were going to say like a month, and I would be like, "Wow, that's really impressive."
It's very, very fast. But in the way, even in instructional design and technology, where we discuss rapid prototyping, this applies to manufacturing and design as well. So we had the first parts out of the machine within days. Again, we started with a community design, and that had the advantage of being looked at and tested by other universities, and pretty much across every industry, there's always instances of monkey see, monkey do. So if you know that somebody is using this or leveraging those tools elsewhere, it gives you some sort of standing to say, well, we're looking at that too, and if it worked for them, it might work for us, and we can apply their same logic to that. So we were getting the first prototypes off, but obviously we continued to improve that over the course of about 2 weeks.
Gotcha.
Within that window, within that 2 week window, we produced our first 1,000, and it was 18-hour days for quite a while to do that. They weren't standard work weeks, but they were. We were obviously really wanting to help solve.
So
the problem.
How much does that printer, the printer that makes these things, makes those masks, how much does that cost? If I were going to, how much does that cost?
So the printers that we use are about $3,000.
Wow, that's pretty inexpensive for what?
Really?
For manufacturing. I mean, you're literally manufacturing.
Absolutely. So these are, we use a higher end printer, a higher end desktop printer. The product line is from a company called Ultimaker. And we use them, mainly they also provide a lot of the software that works as well, which gives us a somewhat vertical one number to call for support kind of experience. But this uses a very similar methodology to what $500 printers use.
And
obviously,
how long does it take to produce one mask, and how many masks can a printer print in one day? Like, I assume you were using many printers, right? Is that how you did this?
So Duke has, and within our labs, we have 3 labs that comprise our ecosystem, and then we have 2 other very close sister labs within the School of Engineering. I represent the larger university as a whole for the full technical experience. Where there are 2 other dedicated labs and a number of smaller research labs that serve specific constituencies. We're across all of those labs. We have about 120 3D printers.
Oh wow!
same middleware. So we are one of the largest deployments of 3D printers in higher ed that we're aware of. So there's quite a few here, quite a few to leverage. For this specific project, we leveraged about 60, and those shields can be divided up into a couple of parts. There's what we call the face frame, which you can see from the pictures here, are actually the part that wraps around. That's 3D. Clear part is what we were laser cutting. To 3D print that face frame is about a 7-hour print. So we're able to get a few in the same day if we were running rotations. And the laser cut part is about 2 minutes. So we produce this fairly quickly. And then there's an elastic strapping that happens as well. There's 2 plastic clips on that we're producing in-house. Each one of those come out of the machine at a rate of about 300 per hour. And then we have a robotic strap cutter that will advance the elastic strapping and then cut those materials. And of course, when we started this, we had very limited feedstock selection. So the plastic that we're using was, it wasn't a case of what plastic do we want to use.
It's what you have, what's available, what you can get, right?
Exactly, which is a very different experience from how I've prototyped other projects before.
Sure.
So
how many people would you say, just to make this face shield happen from start until you were ready to test it with that group of 30 doctors and nurses, how many people were involved in that project?
For the first part of the testing there were about 3 of us that were involved. So once we moved through the prototyping phase and into the full bore manufacturing of it, we produced about the first 10,000 or so with that small group of 3. And then we've expanded to larger lab networks. So we have right now, at this very moment, there are probably about 20 people working for this. Wow. So we have about 5 different lab technicians that are running laser cutting machines right now. We have another 4 or 5 lab technicians that are doing other production work, such as that strap cutting that I mentioned. And then we have a local manufacturer that we've engaged that has another 5 or 6 people.
And you guys aren't just developing these face masks. What are some of the other products that you did develop in this like throughout over the last month and a half, 2 months? What are some other things? And do you have anything coming up? Like, are you guys working on something else? Like what? Just real briefly, just tell me about some of the other stuff you guys have developed.
So some of the other things, probably our largest project has been a project that we call 3D Shield. This has led to publication intellectual property for the university. So it's always exciting to participate in things like that. There are suits for devices that they call PAPRs, P-A-P-R. And you can see the photos of that here. And this is basically a powered respirator suit. When you think about how protection happens, as we've come to learn throughout this project, oftentimes the protection is simply a one-way street. So doctors wear these PAPR suits, in essence, for the purpose of preventing infection during surgical procedures. So if you think about, the classic example of the surgical mask, it's not there to protect the doctor, it's there to protect the patient. But we obviously want to expand protection to go both ways. We're able to convert these PAPR suits. In this case, it's a Stryker flight suit to be able to filter that intake air as well as the air that's leaving the suit. So it's not just protecting a patient during surgery, but it's actually also protecting the doctor doing the work. So this opens up other advanced procedures that can now happen again with that 2-way protection street. We're basically using this PAPR suit backwards as a simplification of that. And that required a lot of work to be able to design that and test that. And those parts were completely 3D printed. There was no other method or process used for those. We ordered, when this all happened, we ordered multiple 3D printers on the spot to be able to specifically to produce this project. So that was exciting. We have a few other ones that are happening. So we have folks that are doing research for aerosols. They're attempting to detect COVID aerosols within the health system. We're able to design and print and produce brackets to hold it. It sounds like a crazy problem to have, but these are sitting on little tripods and they get kicked over all the time.
Wow. So you're simply just developing something like a holder.
And I mean, these are very real problems, but we're able, the cool part about those stories is we're able to produce those we're able to design and print and have part in hand the same day.
Yeah,
And
that's what's amazing about this whole thing is that you're able to go around like the whole manufacturing process and just do it really quick to solve a very simple problem.
absolutely. And then there's other projects. I believe you see the video there, the hand sanitizer stand that we've been working to produce. And this was just a prototype concept. But, we obviously know hand sanitizer is great, but there is supply chain problems with hand sanitizer.
Yeah.
But you can't just buy it anywhere at this point. And with true American ingenuity happening, we've seen distilleries convert their operation
Yeah.
to hand sanitizer production units. The problem that we have there is that we have a limited range of acceptable formulas with that. So the World Health Organization has published 2 formulas. They're both very thin consistency, low viscosity. Alcohol just has no structure,
Sure.
so it just runs everywhere. So we have to apply it with spray applicators, for example. And there's, if you use like some of the other traditional lotion type dispensers, they can actually siphon quite a bit of the material out all over the floor. Of course, this is flammable material, so we really have to think through a whole range.
There's a lot of problems to think about when you're talking about hand sanitizer, and all of a sudden you're talking about thin liquid and flames, and I mean, it goes from like a simple thing to like this, like it's a disaster.
Absolutely. And believe it or not, hand sanitizers are actually a vector. If 100 people all put their hands on the same hand sanitizer dispenser,
Obviously, yeah, you're spreading germs.
You're spreading it. So we've actually been working to design foot pedal prototypes and moving those over to local manufacturing.
Yeah, I like that. It's a good idea. Okay, so you've talked about some really cool stuff. This has been really exciting. I just have one final question for you. So I thought all the stuff you're doing is just fascinating. So if I was a high school student or an early college student, or I wanted to change my career and I wanted to do something like what you're doing, how does someone do that?
So the biggest thing, it's like I liken this to programming quite a bit. The best way to learn programming is to program, is to sit down and do it and make mistakes and start with what I also call them hello world 3D prints. The good news about 3D printing and a lot of this technology is it is becoming more accessible every single day. When I was in college, this technology just simply wasn't available. I was a budding engineering student that altered my life path because engineering was so boring. I was spending all of my time designing things that I was never going to be able to see or do. And now you have the opportunity to design and produce things in the same day. And it's such a powerful experience. Though there's cost to it, there are certainly 3D printers out there that are available at a price point most people can afford. We've seen this STEM revolution happening in high schools as well.
Sure.
These devices ending up in STEM-focused labs, in STEAM-focused labs all over K through 12 institutions. So there's a lot of opportunity out there to do that. And in addition to that, it's not just a hardware problem, but the software is significantly more available as well. There's great products out there such as Onshape and Fusion 360 that have no barrier to entry in terms of cost.
So you can just kind of pick up and start using them. Do you need to be like a programmer or an engineer? Or you can just kind of start playing around with them.
Just start playing around with them. And this is where we start to see the bleed over across all of these 3D tools between a whole range of educational paradigm shifts that are happening right now. Where if you can produce a tool in CAD, you can probably also learn to produce a tool or produce some sort of digitally sculpted product. And you're going to be able to learn to animate it. So we see these connections between media arts and between not just form and fit mechanical engineering, but a whole other range of disciplines. And then you can start to even bleed that over and make extended connections into esports and some of the other things that I know you're interested in as well.
Yeah, absolutely. Well, thank you for your time, Chip. I think that was really, really, really interesting. I'm really excited to go in and kind of explore more like about 3D printing now, just after learning about the process. Like I didn't know as much about it as I did before, we had this discussion. So I'm really fascinated by some of the stuff you guys are doing. I think it's really neat. I'm really excited to see like what you guys can do in the future. Cause I think that's just amazing that you were able to sit down, come up with this idea of these face shields. Just unbelievable to me that, a resource such as a university that we didn't even really think of before COVID to do something like this is helping our medical personnel stay safe during world's worst pandemic that we know of so far. That's just amazing. So it was really great talking to you.
Absolutely. Thank you for having me. I really enjoyed the conversation.
Yeah, no, definitely. All right. I will see you later. Thank you.